Let's explore the inner workings of databases, focusing specifically on the query engine. We'll dive into how database systems process and optimize queries to efficiently retrieve and manipulate data. The database icon visually represents our journey into the heart of data management. The query engine architecture comprises three core components. First is the parser. It performs SQL syntax analysis and validation. Then comes the optimizer. It generates query plans and conducts cost analysis. Finally, there is the executor. It handles physical query execution and data retrieval. The SQL parser performs syntax analysis and validation. Here's an example SQL query that selects a user's name and the count of their orders from the users and orders tables, joining them based on user ID, filtering by active users, grouping by username, and having a count of orders greater than 5. The parser operates in the following 3 steps. First is lexical analysis, which involves breaking the SQL into tokens and keywords. Second is syntax validation, where grammar rules and structure are checked. Third is abstract syntax tree generation, during which an AST is built. The abstract syntax tree is a parse query structure. The root node could be something like select, and then you have branches for columns from and where. Columns can further branch out to specific column names like username or aggregate functions. From branches out to the table names, and where branches out to condition. The query optimizer uses a cost-based optimization approach. Follows 3 steps. First, plan generation, where multiple execution plans are created. Second, cost estimation, where I/O, CPU, and memory costs are calculated for all the execution plans. Third, plan selection, where the lowest cost execution plan is selected. Here are a few cost factors listed. Sequential scan, which has a cost value of 1,500. Index scan, which has a cost value of 125. Hash join, which has a cost value of 350. Sort operation, which has a cost value of 280, and the total estimated cost is 755. Here's a comparison of 2 execution plans, which are alternative query strategies. The first one is the optimal plan, an index-based approach with a cost of 755. It involves these steps. 1 index scan on users. 2 index scan on orders. 3 hash join. 4 filter active users, and 5 group and aggregate. The second one is a suboptimal plan, which is a full table scan approach with a cost of 3,450. It involves the following steps. 1 full scan users table. 2 full scan orders table. 3 nested loop join. 4 filter active users, and 5 sort and group. The query executor operates via a physical operations pipeline. First, a scan which reads data from storage, which might involve an index seek on users table using a B-tree. Then a join, which combines relations, possibly a hash join on user ID with a 64 kilobyte memory buffer. Finally, an aggregate, which groups and computes using a group by with count using a hash table. There are 3 different implementation strategies for join algorithms. The first one is the nested loop with the complexity order of n times m. It's a simple implementation with no memory overhead, and it works with any join condition. It is best for small datasets or when one relation is very small. The second one is the hash join with a complexity of order of n plus m. It builds a hash table on a smaller relation and probes with a larger relation, and is fast for equality joins. It is optimal for large datasets with equality join conditions. The third one is the merge join with a complexity of order of n log n plus m log m. It requires sorted inputs with a linear scan after sorting, and is memory efficient. It is effective when data is already sorted or has indexes. Let's compare B+ trees versus hash indexes. First, B+ tree index. It's a balanced tree structure that supports range queries and ordered data access, with a log n search complexity, and is sequential scan friendly. Point query performance is order log n, range query performance is order log n plus k, and insert or update performance is order log n. Next, hash index, which is a hash table structure that offers fast equality lookups, but no range query support. Constant time access but no ordered access. Point query performance is order 1. Range query is not applicable, and insert or update is order 1. Here's a summary of what we've discussed about the query engine, including the optimization impact on performance. Key takeaways are: first, the parser validates and structures SQL queries. Second, the optimizer chooses the most efficient execution plan. And third, the executor implements physical operations. All of these lead to a significant performance impact, resulting in a 5 to 100 times query speed-up with optimization and an 80% reduction in I/O operations. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.